Okay, I'm Shane Mill. I'm from the National Weather Service. I'm here presenting with Steve Olson. We're exploring cloud backends for the new OGC API environmental data retrieval. So skipping ahead, the OGC Edr API background. In general, OGC API standards define modular API building blocks to spatially enable web APIs in a consistent way. They're all based on the Open API specification, and they're organized by resource type. The EDR-API standard, it defines two goals. One, to allow clients to retrieve a subset of data created by the API in response to a standardized coordinate-oriented query pattern, and then to provide building blocks allowing for construction of more complex applications. This is just a quick overview. Basically, the EDR-API acts as an abstraction layer between disparate data formats and systems. We homogenize the data together. The EDR-API handles that and then describes the data in self-describing URLs, structured URLs. We have schema support for different formats, CRSs, interpolations, etc. Ultimately, we're getting to the means to the end for a feature extraction from a sample coverage. So what do we mean by that? In this situation, we're focusing a lot on meteorological shapes. So we want users to be able to query data by a position, radius, area, cube, trajectory, and corridor. Meteorological data is multi-dimensional data, so that lends well to using the Pangeo. Can you guys still see my screen?
I think it just vanished. Can you reshare again?
Yeah, yep. Okay, are we okay now?
Looks good.
Okay, good. So the Pangeo stack is used on the backend for the multi-dimensional data. Ryan did a great job going through this, so I'll go ahead and skip ahead. So a lot of our meteorological data will come in NetCDF or GRIB. So this is just an example of, for the GFS model, we have a bunch of GRIB files that come in. We can concatenate that into Xarray dataset. That's where we do a lot of our manipulation of the data. We choose to organize our data in a certain way. For the GFS, we're organizing the data by common dimensionality. And then we're storing that in S3 or Lustre or on disk using Zarr. And we're chunking data in the process based on how we expect our users to query the data. So with that ingest process in place, we have these different Zarr data stores in place in S3, and the EDR-API on the fly, based on user query, will select that specific collection from Zarr, load that back into Xarray. We'll do our trimming and slicing, and then we have some modules that connect to Xarray to output in NetCDF, GRIB, JSON, and so on. The EDR-API specification, it provides complete versatility in how you construct your collections. So we tend to base it on use case of how we expect our users to create the data. This first use case is basically a point and click map for selecting weather parameters. So it's basically just a position query. So we know our X and Y chunks will be very, very small to limit how much data that you're loading. So we want to keep the chunks small for optimized performance. But with the GFS, the queries vary quite a bit with like area queries, corridor queries, and so on. So as Ryan explained before, you just have to find the right trade-off for how you organize your data on the back end to optimize performance on the front end. I have a quick demo. I want to hit three main points. The EDR-API accessing the National Water Model River Stream archive. That's in big data program S3 bucket. It's terabytes of data, and I want to show how, and it's in Zarr, I want to show how Dask can load that data asynchronously in a pretty optimized way. We have a GFS collection stored on a Lustre file system. That's also chunked in Zarr. I want to show the effective trimming and slicing of that, and then basically bring two OGC APIs together, the process API and the EDR API, and show how they can integrate with the Zarr backend. So on to the next slide. Here's basically a screenshot of the Dask dashboard in action. This is basically hitting the S3 bucket that I mentioned. This is 6 months of hourly data being loaded in 6 seconds. Without Dask and the Zarr chunking, we just simply could not have that type of performance before. So this is pretty impressive to hit a time series for a position query and get this type of performance. Now I'm going to back out and load my browser just to show a couple more things. If I zoom in a little bit here, this is an EDR-API endpoint for the GFS model. So here are the sampling geometry types we talked about: position, area, radius, cube, trajectory, and corridor. I'm just going to do a quick radius query here. Let me zoom out just a little bit. You can use this leaflet map, just select a radius on the map. Based on the metadata, we have choices loaded here for the user. So I'll select a temperature for a time series. We have the opportunity to output and coverage JSON, grid, NetCDF, and Cloud Optimized GeoTIFF. So I'll select coverage JSON there. These are multiple isobaric levels that I can select here, and then click Show Data. So what that did is that accessed the Zarr backend data store. It, through Xarray, did the trimming and slicing. Through the user interface, we could just add like a quick palette so you can actually see the data for the different vertical levels and the different times there, and then the different output formats. As I said, you could download grid, NetCDF, and Cloud Optimized GeoTIFF, and then bringing it all together. Here's basically a client that we've developed different computational and derived processes for the process API. The client will basically access that process API for this specific computational class. So I'm going to demonstrate a threshold here. This is a dropdown for the EDR-API available collections. So I'm going to select the GFS surface level collection. I'll select an area for temperature, for a model runtime, and then for a time series. And then on the map, I could just select an area.
Shane, we lost your screen again.
Yep.
Yeah, it keeps.
Shane, can you please reshare?
For some reason.
Yep.
So then there's the area on the map. What happened was the EDR API went and found the min and max of the data there, and now the client is creating threshold values. So if I select 280 Kelvin, this is now hitting the OGC API processes and just giving you the data that meets the threshold. So I'll just quickly add a palette there. So you can see the data on the map there that meets the threshold. We can add basically a contour for the polygon that meets the threshold. And what we're able to do here, you can see the outline there. We could download the data in coverage JSON, NetCDF, PNG, Cloud Optimized GeoTIFF, which will hit the process API. But then we have a GeoJSON output too. And then to end this here, you can see that using the GeoJSON playground, you could just load, and let me zoom out a little bit. You can load that polygon that met the threshold. So this is basically just integrating the EDR API and process API together to add a few more insights to the user and a little bit more capability, treating the OGC APIs as building blocks, and all of this with a Pangeo stack type of backend. So with that, I'll end the presentation, and any questions or comments, please hit me up on Gitter.
Yeah, thank you, Shane. And yeah, everyone, please head to Gitter for the questions. And